Okay, so thanks. Today we'll talk about the hydrodynamics of non-integrable and non-abelian spin chains. Particularly, we'll focus on a recent debate. This is work appeared actually with Xiao Chen, Luca de la Cutas, Andy Lucas, and Rahul Nankishore. So after a sufficiently long time, finite temperature interacting systems generally lead to what we call thermalization. So one main consequence is that the only surviving degrees of freedom are conserved charges. And based on this assumption, hydrodynamics will dictate the universal behavior of these degrees of freedom. In particular, it will fix the functional form of correlation functions at low value. So today, the goal will be to address, like I said, an ongoing debate on the long-time dynamics of non-abelian, non-integrable spin chains, where we expect the hydrodynamics or its generalizations are a good framework to address this issue. So this debate in particular concerns SO3 symmetric classical Heisenberg model. The debate started in the 80s. So by classical SO3 symmetric Heisenberg model, I mean this Hamiltonian. So this is defined on a chain. So I labels the side position, and then on each side I have a classical spin vector with a unit norm, and I just have a nearest neighbor interaction. So recently, this debate was revived in a recent paper from this year, which proposed that in the infinite temperature limit and at half filling, meaning no magnetization, spin transport is super diffusive. So the general expectation from hydrodynamics is that the two-point function of the spin, I will say more later why, decreases in the long time as 1 over square root t. And now these people say it looks like there is an additional logarithmic correction, which goes quite a bit against the expectations from the naive expectations from hydrodynamics. Okay, so why?
What does half filling mean?
Yeah, just that the background density of spin is 0. So no magnetization.
But I mean, what does it mean to fill a spin?
Yeah, so this is an expression which is commonly used in spin chain literature. But yeah, all it means is simply, yeah, the expectation value is 0, of the background charge is 0. Charge meaning, I guess, so the spin constitutes an SO3 charge. So in that sense, I guess you can call it.
So does it just mean that the expectation value of S is 0?
Yes.
Okay, or S3 or something?
All the components of the spin.
Okay.
Yeah, that's important. It only happens in this condition. So why is this important? Well, if that's true, it will constitute, of course, a new universality class. Because this was not really observed before. It's not assessed. Moreover, it's interesting because it happens only at the SO3 symmetric point. So by SO3 symmetric point, I mean, you see, so this is an isotropic interaction. But if we add, say, another term which breaks the SO3 invariance, then this logarithm is washed off. So one might suspect that there is a symmetry enhancement argument to come up with it, to argue for this logarithm. And another motivation, which for me was the main reason why I got curious about this, is that it goes against the standard expectations of hydrodynamics in low dimensions, in particular fluctuating hydrodynamics, which is a sort of extension in a sense. I will say much more later. So in this talk, I will basically test this statement from the perspective of hydrodynamics and non-equilibrium effective theories. Okay, so here's the outline. So I will start by giving more details of these hydrodynamics of the classical Heisenberg model. And then I will explain what this fluctuating hydrodynamics is, and I will give context, I will give examples. And then I will briefly introduce the framework, which I will then use to test this claim of the logarithmic enhancement. Okay, so good. So let's start with our classical Heisenberg model. This is widely believed to generate non-integrable dynamics. It's believed to be chaotic. So particularly, like I mentioned, there is an SO3 invariance. So the Hamiltonian commutes with the total spin, with all the components of the total spin, which means that if we wait a sufficiently long time at a sufficiently high temperature, there will be a locally conserved density, which we define as the average, basically the sum of all the spins and then average. This is the system length. And then, so the hydrodynamics here will simply be the conservation equation for this SO3 density. So I have time derivative here, and then I have a divergence of an SO3 current, which I expect to be a local expression in the density and its derivative. Good. So again, I'm assuming here that in the long time, only conserved quantities are the surviving degrees of freedom. This is central assumption of thermalization. So I should include energy density really, but I will ignore in the remainder. One can show that what I'm going to say will not really change much if I include energy density. So now let's see. So the simple approach, the basic approach of hydrodynamics here tells us, so we write down in a derivative expansion a local expression for the current of this SO3 charge. And this local expression should depend solely on the conserved quantities. So it depends on this NA, where A denotes the flavor SO3. So the leading term is very simple. This is just a fixed law. It will be responsible for diffusion. So if I stick just with this term, I plug it in my conservation equation and I get a diffusion. Standard. And now from this diffusion equation, I can immediately infer that the two-point function, the long time of my SO3 density decreases as a 1 over square root t. And then I have this diffusion constant, which is what appears here. So this is a basic dependence. Now in this recent paper, again, it was claimed that we have this logarithmic enhancement, which equivalently can be stated as saying that the diffusion constant is actually not a constant and increases logarithmically in time with this particular power. So this looks like a naive, like a breakdown of the naive local hydrodynamics. So we want to understand what is the cause, besides to check whether this statement is correct. So regarding possible causes of these logarithmic enhancements, one could wonder if this is due to the non-abelian nature of these hydrodynamics, the non-abelian nature of the flavor symmetry, or whether it could be due to hydrodynamic fluctuations. I will explain more these starting from the next slide. Or whether there are additional emergent charges, which I didn't consider. Additional besides SO3 and besides the energy. So now in the remainder, I will address these 3 points using the framework of non-equilibrium effective field theory, which will prove to be simple and systematic in order to address this story, at least from a hydrodynamic standpoint. Good, so now let's talk a bit about hydrodynamic fluctuations.
Paolo, what was their evidence for the log?
Oh, it's a numerical evidence. You just simulate this two-point function. This is time order two-point function of the spin. And then you indeed, yeah, this you will get after the thermalization time.
But determining a log numerically is a very tricky business. So how robust is their analysis?
Yes, so that's a good point indeed. So indeed, one thing one could do is just we numerically simulate it. We see whether we detect it or not. Depending on how many people get it, perhaps we can call it consensus. But what I will show later is that this logarithm can be, at least again using hydrodynamics, can be explained in terms of power decay of other correlation functions where we don't care about the logs. So there would be a much more robust argument. So depending on how, I will explain this in detail, but depending on how these power decays will behave, then we'll be able to tell whether this logarithm is consistent or not with our findings, as far as hydrodynamics is concerned.
Okay.
Yeah. Good. So hydrodynamic fluctuations. So what are these fluctuations? Well, we are dealing with many body systems at finite temperature. So inherently there are just stochastic fluctuations due to the fact that we are at finite temperature. And in principle, this could also be linked to quantum fluctuations, although here I'm dealing with the classical system, so they're not important in this story. Now, these fluctuations are well known to drastically change the long-time dynamics. Even by drastically change, I mean that if I just use the naive predictions from the hydrodynamic equations, so the hydrodynamic equations, like I showed, will predict this 1 over square root t. But then it so happens that if I account for these fluctuations, they can qualitatively alter the time asymptotics. Let me show now. So okay, here is an example. So okay, first of all, this was realized. As far as I know, the first paper realizing this was numerics, and it was from end of the 60s. Now here is a numerical plot from a molecular hydrodynamic simulation, where we see that, contrary to the predictions from standard hydrodynamics, so this is the decay of the velocity autocorrelation function, and this plot shows consistency with the polynomial decay, which scales like t to the -3 halves. So this power is entirely due to fluctuations, and this is the leading decay power for this particular two-point function. Okay, so in the long time physics, this is really important. And I'm now going to show a basic list of examples where, where this really changes dramatically transport properties and scalings in the far IR. So the first example, which is probably the one known for the longest, well, okay, one of the longest known, is about just ordinary fluids with translational invariance. So this was known from the 70s. So this paper was about diffusion. So this is like the baby version of what happens here. And then a few years after we had, ordinary fluids with translation invariance. So if I'm at sufficiently low dimension, fluctuations will be more important, as intuition would suggest. And in particular, what these papers found is that for various dissipative transport coefficients, one can observe divergences with the system size. For example, in 2 spatial dimensions, the charge conductivity, the heat conductivity, and the shear viscosity, they diverge with the logarithm of the system size. So this, again, this goes against the naive hydrodynamic setup. Then in 1 dimension, the divergence is even stronger. It grows like a power to the 1/3, which is a signature actually of this famous KPZ universality class. Another example is in the context of spin chains. So it was quite recently appreciated, first in this paper, numerically, that if I consider integrable SU2 symmetric spin chains, again at half filling, I will observe KPZ spin diffusion. So spin diffusion, standard spin diffusion, is just omega goes like k squared, which is related to this 1 over square root t that I mentioned earlier. So here we see an enhancement which goes from the power of 2 to 3 halves. So there are some sort of relevant fluctuations which change my IR scale. And only recently there were papers explaining theoretically the emergence of this scale. Still about spin chains, another context is with actually non-integrable spin chains, which possess almost conserved quantities. So strictly speaking, this is not exactly hydrodynamics, but say, as far as I limit my study within a finite but long time window, I will observe approximately conserved densities, which in turn lead again to this type of scaling. But the nice thing here is that the systems are non-integrable. And then another situation which we analyzed recently is that in the presence of chiral anomalies, this KPZ scaling also can arise. So, so one example is chiral surface metals. And actually it turns out that depending on dimension, the scalings are exactly the same as in this situation, where the difference is that here we need translation invariance, whereas the scaling here does not need translation invariance. However, we need a chiral anomaly. So the take home so far is that from the point of view of these fluctuations, anomalous transport, meaning relevant scaling, these divergences or these lower power, this anomalous transport to emerge requires the presence of one of these properties. Translation invariance, like in ordinary fluid conserving momentum, integrability, like in these spin chains, or chirality, like in this example. So none of these properties is manifest clearly in this system. Like I said, it's widely believed to be non-integrable. Definitely it doesn't have translation invariance, and not to mention, yeah, chiral anomalies. So what's happening here? What's going on? Good. So to address this business, I will now very briefly introduce the framework of a non-equilibrium effectivity theory. So I will be quite brief here because I think I discussed this several times before. Nevertheless, so let me just explain the general idea. So we are interested in correlation functions in the long time regime, long time differences, where the initial state of the system is a mixed state. So we're not in the vacuum. We will be interested in high temperature thermal state. So this is the type of correlators that we want to study. Let's make explicit the factors of the evolution. So now these operators are showing the picture, and I'm just making explicit the evolution time. So we see that time here runs from -infinity to +infinity, and then it goes back from +infinity to -infinity, with backward evolution. If I rewrite these evolution operators using path integral the usual way, then I find the path integral over a doubled set of degrees of freedom. So here, psi1 and psi2 is a doubled copy of the microscopic degrees of freedom. It could be, say, just my spin written in a coherent state basis. This factor of the measure, so S is the microscopic action. So this stands for the forward time evolution, and this stands for the backward time evolution. And then I just have my operator insertions. So this can be represented conveniently in this picture, in this Schwinger-Keldysh contour. So the upper segment stands for the forward evolution, the lower segment backward evolution. So I can put my operator insertions in the backward and the forward time segment. And then At the initial time, I place my boundary condition for the fields, and the final time, I identify the fields. That's because I'm taking the trace. So I want now to use this general setup to do basically write down an effective field theory for my classical Heisenberg spin chain. Now, how do I do that? So imagine that in our problem, we have a good separation between fast and slow variables. In the current case, the slow variables will be the hydrodynamic densities. So these will include the SO3 density as well as the energy density. And then I have fast degrees of freedom, there are everything else. So formally speaking, I can imagine integrating out the fast degrees of freedom and from this Schwinger-Keldysh action and obtain a simpler path integral written just in terms of the densities of the low energy modes. And I will have a local effective action here. Okay. So this effective action, of course, is local because I have a good separation of scales. And moreover, it does not have a factorized structure like this. That's because that's an effect of integrating out the fast degrees of freedom. Fast degrees of freedom are coupled through the boundary conditions here and here. And integrating them out will generate instantaneous couplings in time, as I drew in this picture, so that I don't have factorization. Now, this step is very hard. It's just, I'm writing it as a formal step. So what we do in order to proceed is we will use the approach of effective field theory. So we don't know the explicit form of the action, but we know a long list of properties and symmetries that these actions should satisfy. So after listing those properties, one simply writes down in a derivative expansion the most general set of terms that are compatible with all these requirements. And that will constitute our fluctuating hydrodynamics description. In this case, for the Heisenberg spin chain. So some of these properties come from unitarity. Some of them come from the fact that the initial state is locally thermal. And then, of course, we will have a bunch of symmetry requirements coming from the fact that we are interested in the effective field theory for the conservation of the SO3 charge. I'm going to skip, so I give a few details here about the ingredients on how to implement this action principle, and I'm skipping these details. Let me go directly to the final product. So again, we are interested in the conservation of SO3 charge. And after the dust settles, we end up with a local action whose Lagrangian, we don't need to worry about the explicit expression. But so the degrees of freedom here are is SO3 density. So again, this guy lies in the adjoint representation of SO3. And then, like I said, we have two copies of degrees of freedom. So the partner is this SO3 adjoint field, which we call fluctuation field. I will say in a second why that's the case. So to get some physics out of this Lagrangian, let me directly write down the explicit hydrodynamics that this Lagrangian implies. So let me write down the explicit expression for the SO3 current. The SO3 current will be a local expression in the SO3 density. Here it is. So a leading order, we have a term which we saw before. This is again just a standard fixed law for SO3. So this is just a coefficient, is our diffusion coefficient. It's positive. This essentially contributes like a Magnum type of contribution to the dispersion relation. So it will contribute to the, so this contributes like k square and is dissipative. This also contributes like k square, but it's non-dissipative. So the sign of D1 can be positive or negative. And then here we have, this is basically a nonlinear version of diffusion. So it's like a diffusion longitudinal towards along the direction of the density. It's like a rank 1 nonlinear version of this guy. This 2 is positive, is not negative. And then this term represents the noise, the thermal noise. So this comes from, this is basically the Legendre transform of this field. And it describes, it's a proxy for what I called before hydrodynamic fluctuations. So it's a delta correlated noise in space and time, and its variance is nonlinear and is given by, it's related to the diffusion and this longitudinal diffusion, essentially through fluctuation, through a nonlinear version of the fluctuation dissipation theorem. Good, so this is the physical setup of the fluctuating hydrodynamics, and let's now explore whether this can host a logarithmic enhancement of the diffusion. See if this is consistent with the original claim of the paper from earlier this year. So how to do that? So we need to analyze the scaling. So we need to look for, literally just do an RG type analysis and look at whether the couplings in our Lagrangian turn out to be marginal or relevant or irrelevant, okay, upon choosing the correct space-time scale. So let's do this by steps. So first we look at the kinetic part. We look at the linearized Lagrangian, again expanding around zero background density. This is necessary in order to obtain the logarithm. So if we do this expansion, we find the kinetic term will simply give a diffusive scaling. So omega, the frequency scales like k squared. Now that we know this scaling, which is quoted here, we can also infer the scaling of the dimension of this IR degrees of freedom. So the density and the fluctuation field, they both scale like square root of momentum. And then using these scalings, we can tell the scalings of the nonlinear couplings, which are these D1 and D2. And then we can see that D1 and D2, just by looking at it, they scale with a negative power momentum, which means that they are irrelevant. So there are no marginal, there are no relevant couplings. That means that in its current form, this, the effective path integral for this action will not give any logarithmic correction to the diffusion constant. So far we don't find agreement with the claim. So how can, maybe we miss something. So how can we, what are the ways we can extend this model in order to include the possibility of logarithmic. So it turns out the possibility is the existence of emergent charges, which we didn't consider before. So first of all, let me actually make a short comment about this logarithm. So what are the situations where we already know we know there is established literature on a rising logarithm in the context of a fluctuating hydrodynamics. So one example is in two spatial dimensions with translation invariance, or we call anomalies, but we are in one dimension. Okay? So in one dimension, one known case is related to basically KPZ equation, which describes the surface growth with the reflection symmetry. But yeah, these are certainly unrelated to our current situation. So what we need to do, so the logic goes as follows. Again, we have a Lagrangian. Everything so far is irrelevant. So we need to add a nonlinear coupling, which is relevant. Or equivalently, let's talk in terms of the current. The leading term in the current is this diffusion term, just a linear term. Here we want to add a nonlinear contribution, which has the correct scaling dimensions to make it marginal. And then that will give us a chance to obtain this logarithmic enhancement. It turns out, just by doing counting, that the only logical possibility allowing for marginal couplings is that there are additional emergent charges. Okay. Why is that? So, conserved densities, first of all, scale like momentum to the 1/2. So that's similar to what I obtained here. One can generalize the analysis diffusive. Yeah, this is just a universal result for diffusive densities. So if I want a nonlinear coupling here, yeah, I just do my counting and I find that I should not have derivatives and I should have a cubic term in densities. So if I have a cubic term in densities, this will scale like k to the 3 halves. I just put this, but then it scales precisely like this term. Okay, this is k times k to the 1 half. So in order to have k to the 3 halves, I need to have a cubic coupling with densities and no derivatives. And the only way to have it is that there are additional charges present in these long-time dynamics. So turns out the minimal way to achieve this is to include the 2 scalar charges with some suitable parity and time reversal transformations. And this is how the nonlinear coupling will look. This is guaranteed to be marginal. So here we have, okay, this is so this is the SO3 charge density. Then I have this pi and epsilon t. So as a consequence, our hydrodynamic Lagrangian will contain a quartic coupling, okay, because this is at the level of equation of motion. So that will include the fluctuation field, this pi and epsilon, and the SO3 density. So how do we proceed to confirm that this magic coupling leads to a logarithmic contribution? Well, we just do a straightforward one loop computation with our effective path integral, so that the 2-point function of the SO3 density received a self-energy contribution due to this higher loop calculation. So without fluctuations, I just neglect sigma, and I will have ordinary diffusion 2-point function. So anyway, this sigma, so the structure of this sigma is indeed involves these 4 field couplings. So I have a 4-leg vertex. So this thing will be proportional to lambda square. And then indeed, it will lead to a logarithmic contribution to lead to a self-energy which is proportional to k square times a logarithm omega. So I can interpret this as a logarithmic contribution to the diffusion. So now one can do, so basically this leads to a beta function for the diffusion constant, which by solving it will lead to basically a resummation of the leading logs for this, for this kind of loop correction. And the answer we get is that the diffusion constant will grow as the logarithm of time to the power of 1/2. So this smells a bit like the logarithm we are after, except that the logarithm that those people found had a different power. It was a power to the 4/3. Here you have 1/2. But at least this serves as a proof of principle that it is conceivable that having additional charges, we may find this logarithm. So good. So good. So this is the general perspective. Let's now understand whether indeed we are missing some charge. Let's see whether indeed we have some smoking gun for this mechanism to happen. So in the continuum limit, indeed there is an additional charge. It simply trivially arises from translation invariance. So this is usually called the torsion, because it can be essentially interpreted as a torsion of a curve generated by the spinning field. I'm not going into details. Anyway, this is called this is what people call it. So in the paper that observed this logarithmic enhancement, the explanation given for it was the emergent conservation of distortion, even away from the continuum limit. But this sounds a bit, it's not quite clear whether this should really be true, because we are interested in the high temperature limit, and it's well known that in the high temperature limit, if we are not in the continuum situation, then there will be typically umkrap scatterings, which will lead to the depletion of this torsion. So we really don't expect this thing to be conserved at high temperature. And this claim about the logarithm was at infinite temperature. So is there a direct way to assess whether this claim is correct or not? For some, like, could it be that for some reason this claim persists, accidentally persists in this classical Heisenberg model? Or more in general, could it be that there are other conserved charges which will eventually lead to this logarithmic enhancement? So we now show numerical test, partially analytic, partially numerical, which we use indeed to check whether there are additional charges. So as I mentioned before, the central assumption of thermalization is that after transient time, after the thermalization time, the only long-living modes will be the densities. So in particular, if we consider a generic, sufficiently simple operator, which is not need to be conserved, the long-time dynamics of this operator will be controlled by the conserved densities. This argument was recently advocated by Luca in a recent paper, and was implicitly used in other recent literature. So usually, this argument is applied to currents associated to conserved densities, whereas here we are applying it to generic, non-conserved operators. So let's see an example. Let's say we have an operator which could be, in our case, a product of the elementary spin variables defined on each side, and maybe derivatives acting on these spin variables. Well, sorry, there are no derivatives. So I guess this product of spin variables located at different sites. So in the long time limit, we expect this operator to be essentially governed by a local expression in the densities, where the leading term is dictated by symmetry matching. So if this operator, say, is odd under parity, and even under time reversal, then the leading order expression, leading in terms of scaling, will be this particular expression here. So we have a single spatial derivative, which guarantees that this expression is a parity odd, so that it matches the parity quantum number of this operator. And then lambda naught is just some non-universal constant, which typically we assume to be non-zero. And then here there will be higher order terms, higher derivatives, or higher products of the charges. Similarly, let's take now a spin-2 operator. So we have two SO3 indices, and then I can again match it in the IR in the long time to a local product of my conserved density. So now this type of matching will determine the scaling of the autocorrelation functions of whatever sufficiently simple operator I'm considering. So how does this work? Let's consider again this operator I wrote here. So I'm interested in this 2-point function. And then assuming factorization, I can predict the scaling of this guy by knowing the scaling of the density-density correlation. Okay, this factorization is possible because we know that from our effective theory Lagrangian, there is no relevant or marginal coupling. Okay? So this step goes through. And then just by knowing how distinct these two guys decay in time, I can immediately tell the scaling of my operator. In particular, knowing that the density scales like k to the 1/2, I can infer that this operator scales like k squared. In particular, this means that that this function still has a power decay, despite its O is not conserved, but the decay power will be much higher than the time decay of the density. In particular, the density, again, decays like 1 to the square root t. This guy decays like 1/t squared. So we will use this approach so we will basically simulate numerically 2-point functions for a list of operators which exhausts all the symmetry sectors of our Heisenberg model. And if the decay powers match the predictions from our vanilla fluctuating hydrodynamics, that will mean that there are no additional conserved charges. Instead, in order to see additional emergent charges, we will have to detect, so we will have to see that at least one correlator will decay more slowly than predicted by our model. So again, this is just comparing power decays. There are no logarithms in this search. So it's much more clear-cut. Much more clear. So in particular, we simulated the decay of operators belonging to 12 different symmetry sectors. So these sectors are labeled by parity, time reversal, and spin SO3 representation. So we simulated the first three representations: spin 0, spin 1, and spin 2. So an example of a microscopic level of such operators, so it could be just the spin evaluated on one lattice site, which obviously should be meshed in the long timer with the SO3 density. Another slightly less trivial example is this sort of cross product of the spin, which should be matched by matching quantum numbers, should be matched to the gradient of the SO3 density. Okay, so these are some beautiful plots done by Xiao. So let's see an example here. So again, in these plots, we have a log time representation of the decay of these log time representation of these 2-point functions. Again, these are expected from our model to decay as a power law with some power gamma. The powers gamma are estimated here. So let's take, for example, this minus case. That's the yellow line. So the yellow line has a slope of 1.5. So that's gamma. Now let's see if this matches our prediction. So the microscopic operator we simulated in this sector is written here. So this is negative eigenvalue with respect to time reversal and parity, and clearly it's spin 0. So our hydrodynamic theory tells us that we should match in the continuum with the gradient of the energy density, and then so the energy density is case like k to the 1/2. This case like k, so we get 3/2. So we predict gamma equal to 1.5, which is precisely what we observed here. So one can repeat this simulation for all the other symmetry sectors. So we see that quite a few plots actually have pretty wide fluctuations. So it's not very easy to estimate the power decay there. But what one can say for sure is that the power decay is definitely greater than 1/2, which is what we expect if an emergent density couples to these symmetry sectors. So as you can see here, all the decays are definitely greater than 1/2. So in particular, this plot here shows that this torsion, which was argued to be conserved in the literature, is actually badly not conserved. So this is exactly actually this. So this torsion belongs to the same symmetry sector as this. It's in the minus symmetry sector. So our hydrodynamic theory predicts 1.5 decay, which is precisely what we find. So that means absolutely there is no conserved tau. So even though there could be some logarithm, definitely the explanation proposed was clearly wrong. But now on top of it, since we explored all the symmetry sectors, we can conclude that as far as hydrodynamics is concerned, we expect that in the very long time limit, this logarithmic enhancement should disappear. Unfortunately. But at least here we have a clear numerical evidence. So another nice example. So we we repeated this analysis for some variants of the classical Heisenberg model. For example, here we have a random Heisenberg chain where the coupling is random both in space and time. Particular energy is not conserved. An interesting situation is when this J can take uniform values between an interval which is symmetric around 0, which gives rise to an additional spin flip symmetry, which wouldn't be there in the classical Heisenberg situation, with the non-random situation. And again, we observe, so these power decays are, some of them are actually faster decays than here, and that's a consequence of this additional symmetry. And moreover, one can actually show that this logarithmic enhancement, at least within a finite time window, exists even for this random model. But nevertheless, we still didn't find any emergent conserved quantity. So our predictions precisely very neatly match the numerics. So we essentially conclude that in the very long time limit, where we expect the hydrodynamics to give a complete description, the logarithm is expected to disappear. So let me show now a plot of our simulation direct in terms of this spin-spin diffusion. So here I'm plotting using, again, logarithmic time scale. This is the plot of the diffusion constant as a function of time. The orange plot is energy diffusion. And we see that after the thermalization time, which is around this value, the energy diffusion constant essentially saturates as it should be, as expected. Whereas the spin diffusion constant, indeed, even in our simulation, we observe a pretty long growth. So linear growth here signifies logarithmic growth. However, it's not clear whether this logarithm really will persist at late time. I could say there is a slight bending here. So it probably could be that after some anomalously long time, this guy will eventually saturate some large value. But still, what's still puzzling here is that within some longer, although finite time window, which is still much longer than the thermalization time, the diffusion of spin has not settled in, and indeed we find this logarithmic enhancement. So we're still wondering what's the origin for this logarithmic enhancement. Is it some quasi-conserved quantity, which in principle our approach should have detected? So there is still a little bit of an open puzzle here. But nevertheless, regarding the very long time behavior, we simply expect this curve to saturate into some fixed value. So to summarize, we developed a framework for non-abelian fluctuating hydrodynamics, which we then applied to this ongoing debate on a spin transport in certain SO3 symmetric spin chains. And we concluded that, at least in the very long time, there shouldn't be persistence of any logarithmic growth, any anomalous logarithmic growth in diffusion. So there are a few questions that remain. I just mentioned this long but finite time window where we observed indeed a logarithmic growth. It would be good to extend our analysis to quantum spin chains, because this logarithm actually has been, with the same power, has been observed also in a few other quantum spin chains, And then another potential question would be interesting to understand if this particular power to the 4/3 can be fundamentally ruled out just by first principles from these fluctuating hydrodynamics actions. It's not immediate. This is not an immediate thing, but it's a well-defined question. So if one is able to I mean, I showed that we can have logarithms, but if one is able to exclude that we can have this specific exponent, then in a completely theoretical way, we can exclude without numerics that in the long time, this logarithm will be there. So it'll be sort of more fundamental approach. I think I will stop here.
Thanks, Paolo. Yeah, we have time for questions.
I had a question. So you mentioned how there might be so you mentioned how after some time you expect the logarithm to die away. So where is the time scale coming from that's larger than the thermalization time, but it's still like small enough for the behavior to saturate?
That's exactly the question. We don't know. That's the short answer. Yeah, so naively, so again, the thermalization time is around 10, around 2. Yeah. So there is a pretty wide time window where the logarithm is indeed observed. So within this time window, we would expect that this operator search within numerical would reflect into some anomalously small power decay, which eventually becomes, after this anomalous time window, it will become the decay that we predicted from hydrodynamics. But for some reason, we didn't see these almost conserved charges, even with our numerical approach. So it's quite puzzling. As far as I know, even the spin chain community, the original belief was that indeed there could be some quasi-conserved mode, but in principle, our analysis should capture that. So it just made the puzzle even more confusing. Another possibility could be, this is not about hydrodynamics, and it could be that the spin diffusion constant, the true spin diffusion constant, the one that saturates after very, very long time, has some weird non-analytic dependence on the spin density. So that in a sense, the effective theory should really not be local, but it has some, say, non-analytic dependence on the degrees of freedom on the spin density. That could also be an option. So yeah, that's a direction which should be investigated. That's the only alternative I could think of so far.
Are there any more questions? I may stop the recording, but everyone can stick around.